Statistics, these are the notes for 10.1 and 10.2. We are looking at linear correlations in this chapter. The idea here is that if we look at some paired data, so it has like an X and a Y in it, if I plot the data and it looks fairly close to being in a line, we'd call it a linear correlation. There's some line of best fit, also called a linear regression line, that can closely match that data. On our notes here, realize that what we're saying is there's a correlation between two variables. It does not, however, imply causality. That's an important point. Just because two things seem to be related to one another, it does not mean that one causes the other. There could be some third effect that's making both of them change. So just because if I had height here and weight here, if it's true that as height gets bigger, as height goes up, weight goes up, hence a positive correlation, that doesn't necessarily mean that being taller makes you heavier or being heavier makes you taller. So we cannot assume causality. That's when you'd have to perform some sort of experiment to justify causality. Again, in this chapter, we're going to be focusing on linear correlations. There can be others. We could have some sort of exponential correlation. That's not linear, but it's definitely a correlation. We could have some sort of parabolic correlation. So other things can happen, but we're going to focus just on linear. Now, the linear correlation coefficient is going to be the variable R. And it basically is a measure of how strong the linear correlation is. So what does that mean? Well, if my data points are pretty much in a perfectly straight line going uphill, let's say they're perfectly in a line, this would be an R value of 1. 1 is a perfectly straight uphill line. Vice versa, if my data points are in a perfect line going downhill, that's still a perfect correlation. It's a perfect correlation of -1. So -1's not bad here. -1 still means linear. It just means downhill. +1 means linear uphill. Pretty much most data will not fall perfectly in line. It's going to be somewhere in between. So in general, the closer I am to -1 or 1, the closer I get to either -1 or 1 means more linear. Meaning right in the middle, 0, this means less linear. So closer I am to 0, bad. Closer I am to 1 or -1, better as far as a linear correlation. Now, I have this really nasty formula down here. Oops. Do not worry about this formula. You do not have to use it. It's mainly there to scare you. We're going to be using StatCrunch to figure out the R value, but there is a formula to it. I just wanted you to be appreciative of how much work StatCrunch is doing to give us this R value. So here's some scatter plots and their correlation coefficient. 0.851, that's fairly close to 1. So that is fairly linear and uphill. -0.965, that's really close to -1. Again, that's still good. It just means downhill being negative. That's really close to being a line. Letter C is a correlation of 0. Again, that means not linear. And you can tell it just looks like a splatter. On letter D, this has a very good correlation. It's just not linear. That would be a parabolic correlation, parabola. So the whole point of letter D is to show you that things can be related, but just not necessarily linear, maybe not lines. So we're going to be using table A5 for this, which is in your packet. We have the critical values. We're testing stuff again, just like we were doing in the last unit. And I'll explain how to use table A5 in just a second. So if the absolute value, keyword there, absolute value, of the computed value of R exceeds the value in table A5, we conclude that there is a linear correlation. So basically, I'm going to let StatCrunch calculate R for me and calculate the value of R. If that value, or its absolute value, if it's a negative, I'll just think of it as a positive. If it exceeds the number in the table, whatever number I'm looking at, let's say maybe I'm looking at 0.602. If my value exceeds 0.602, I say, hey, it's linear. Basically, the numbers in this table are the minimum values that we have to exceed. So they're kind of the benchmarks. So on example 1, we have data for the length of someone's shoe print in centimeters and their height. We're trying to figure out, is there a correlation basically between the size of your foot and how tall you are? We're using StatCrunch to do all this stuff. So I'm using the first column of StatCrunch to be my shoe print length. So think of this like my X's and the heights as my Y's. Basically, it's paired data. So I have it up in StatCrunch here. I put them in columns. So I put my X's in column var1, I put my Y's in column var2. It's very simple to calculate the linear correlation, the R value. I just go stat, regression, simple linear. So stat, regression, simple linear. I basically just tell StatCrunch what column is my X variable. That's going to be in the first one. What column is my Y variable? That's going to be the second one. I don't have to do anything else in here. I can just hit compute. And it gives me a whole bunch of data here. But the part we care about is right here, R, correlation coefficient. So it's about 0.591, we'll say, for my correlation coefficient. So I got R to be 0.591. So the question is that close enough to 1? So 0.591. 0.591 is right around here. Okay, that's pretty close to dead center. Is that close enough to 1, or is it not close enough? That's where I'm going to use the table in our green packet. So I'm using 0.05 significance level. So I'm going to be doing alpha is 0.05. There are 5 data points. Realize it's not the amount of numbers. It's 1, 2, 3, 4, 5 data points, X and Y's. So I'm going to go to N is 5. N is 5. My significance level is 0.05. So N is 5. My significance level is 0.05. So 0.878 was the minimum value R had to have, 0.878. Well, clearly, .591 is not good enough. So it was basically saying my cutoff was 0.878. Anything less than that wasn't good enough. So since 0.591 is smaller than 0.878, not linear, basically. There's not enough evidence to support linear. So the points weren't quite good enough. Also, just an aside here, back into StatCrunch. Once I did all the calculation, it gave me all this data. If I press this arrow, it also plots the point, or plots the points. So I can see I've got my 5 dots. And they try to always draw the best line they can, but you can see that especially these dots here are really far off. So it doesn't look very close to linear. So that does it for that first example. For the next example, we're looking at PSAT scores, the practice SAT versus the actual SAT. Some of you probably took the SAT and the PSAT. We're going to first on this one, though, make a rough scatter plot. I'm going to use the PSAT as my x-axis, SAT as my y's. I've actually already drawn this up. This is just to give me a feel for how linear does this actually look. And let me zoom this out so we can actually see the whole thing. So I made a rough, very rough sketch of where the points are. PSAT on the X, SAT on the Y. And you can see from this, yeah, there's definitely some linear here, but there's some points that look like they might be outliers that might screw this up. So again, by looking at it, it's got a feel of linear, but I don't know if it's good enough. So to make it precise, I use StatCrunch. So again, I'll get into StatCrunch here. Get this lined up for us. There we go. So I've put the PSAT scores down var1, the SAT scores down var2. Again, I go stat, regression, simple linear. var1 is my x's, var2 is my y's. I don't have to do anything else on here. I hit compute. And my correlation coefficient this time is about 0.543. So this time I was, oops, try that again. R was about 0.543. So pretty close to that one we had on the last problem. My R was about 0.543. It's a decimal. Is that close enough? Again, I have to compare to the benchmarks. Oops, wrong thing there. The benchmarks on my table here. They set the minimum values that it has to achieve. So looking at my table, I'm using 0.05 for my significance level again. There were 8 data points on this problem. Going back here, 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to N is 8. So on my table, N is 8. I'm going to 0.05 again. So the minimum value of R to say it's a line is 0.707. Well, darn it. So it had to be 0.707. it was not, oops, that's not what I wanted. 0.543 is too small. Again, 0.707 was basically saying, hey, it has to be here. It has to be here or better for me to say it's linear. 0.543 was not, so not linear. And again, if I, on StatCrunch, click this arrow over, I can see some of the data was kind of fitting that line, but there's a point down here that's not good. These points, they don't feel that close to it. So it doesn't look like it really did all that well. One last important point to mention before I close out on this one is that your table gives you positive values. That's why I said the absolute value of R. Remember, if the data happens to be flowing downhill, I might get an R of, like, let's say on this problem, I got an R of negative 0.902 or something like that. Now you might say, well, negative number is small. Well, yes, but remember, closer to -1 is still close to a line. It's just a downhill line. So basically, if you get an R that's negative, think of it as positive when you're looking at your chart, because the chart only deals with the positive versions, but it's still the exact same. So on this problem, this fake example, getting R to be negative 0.902, that as a positive number is bigger than 0.707, so I would conclude that it's linear. So again, all I'm doing in this section is deciding, is the data linear or not? All right, that does it for the first sections, 10.1, 10.2.